Okay, so today's notes are on section 3.5, population growth and resource availability. So, population characteristics. Let's talk about some of the characteristics that we generally discuss when we're discussing populations in general. And so, the first thing would be the size of the population. The size of the population is denoted with a letter N, and there's a total, that's basically just the total number of individuals in a given area at a given time. So larger populations tend to be safer from population decline, but not always. There's always exceptions to that. All right, so another characteristics of populations that we tend to discuss and that you should know about is population density. Density is the number of individuals in a given area. So we take those numbers of individuals divided by the area. And so an example of that, we would usually talk about population density. If we were talking about a population of panthers, we might say that there's 12 panthers per square kilometer. So population size for this would be just be 12 panthers, but then we look at the density of it and we would add in that area piece. So higher population density tends to equal higher competition. And so there's also a higher possibility for disease outbreak, and there's a possibility of depleting the food source. So distribution is another thing that we tend to look at, and I'm going to get rid of this here. So distribution is how individuals and populations are spaced out compared to each other. So is it random? Like trees, for instance, wherever seeds are dropped, that's kind of where the tree grows. Or is it uniform in something that we might see like territorial animals? For instance, when I think of that, I instantly think of an owl, one of my favorite birds. And they're very territorial. So there's only, if you looked at a woodlot, the 100-acre woods per se, some of you will get that reference, then there might only be one or two or three owls kind of spread out because they're defending and competing within a territory. So that would be that uniform distribution pattern. Or there might be even clumped distribution pattern where you have a herd of animals that are moving through. So I really like these pictures over here. You can kind of see here the individuals represented with these purple dots. And let me get rid of my camera here really quickly so that we can see this fully. So this is a very random distribution. This is uniform. And then here is a clump distribution where we might have like a family of meerkats living here in this little hole system. And then up here we have another clump together distribution. So anyway, that are the three different characteristics that we tend to talk about. Okay, so there's also some characteristics that we discuss, and you also need to know about growth factors. So this has to do with how populations grow. So populations grow based on the sex ratio, the ratio of males to females. If it's closer to a 50-50, then that's a very ideal situation for breeding usually. A die-off or bottleneck effect can lead to a very skewed sex ratio. So if we have a drought that happens to come in one year and totally destroys a food source, and it decreases the population of, say, grazing animals down to like hardly nothing, where there's only a few individuals surviving, you have to really make sure, you probably won't, because it's going to impact the genders, you know, unequal. I mean, it's just going to randomly impact whoever lives and whoever dies. And so you may not end up with that 50-50 nice distribution between males and females. You might end up with something more like 80-20, which could be a problem if it's 80% males and 20% females. Anyway, so sex ratio, that is something that can limit population growth. Okay. Density dependent factors. There's two types of density factors, so it all depends on the number of organisms in the area. But the density dependent factors are factors that they influence the population growth just based on the size of the population. So for instance, if you're in an area and it's got a set number of grasses, let's say, and you want grazing animals to live there, the amount of grass would be a density dependent factor. The population of grass can support, 100 wildebeest. So as long as we're under that 100, then we haven't reached the carrying capacity. Those animals are able to thrive and survive and reproduce and have babies and all of that. But then once the population size sort of exceeds that carrying capacity, then that's a problem. The area won't support the number of wildebeest anymore. The wildebeest have to leave the area. So that's a density dependent factor. It depends on the size of the population as to whether or not that area can be supported with that factor. Okay, all of these things will limit the population growth. So in other words, they all set a carrying capacity. All of these things sort of set that carrying capacity for the population. Okay, small populations don't necessarily experience these density dependent factors, but large populations do. Okay, so density independent factors. These are factors that influence the population growth. It doesn't matter what size the population is. So for instance, any type of natural disaster that can move in and wipe out an area. So I'm thinking of a flood or a hurricane, tornadoes, earthquakes, even fire, all of those things can come through. And it doesn't matter if you had 1,000 organisms or individuals in that population or 20, they're all probably going to be impacted in some way. And so this can actually lead to bottlenecks that we've referenced in the past. And it doesn't matter, like we say, how big or small the population is. It just impacts them all. So you need to know the difference between a density dependent factor and a density independent factor. Make sure that you can describe the difference in those. Okay, so here's an example, another example. And this is good because, again, there's a graph. AP likes to show lots of graphs, data, images, that sort of thing that you need to interpret. So food is a density dependent factor. It's a limiting resource. So when there's twice as much food was added to the dish, both species of this single-celled protus, this paramecium, actually increased by two times. So you can see here when there was under high food conditions right here. Let me take away my picture here. Just turn off my webcam. When twice as much food was there, we can see that they're flourishing. Okay, they do still reach a plateau though, because there isn't a finite amount of food. There's a limit to the amount of food that is available. So while twice as many can survive, they're still going to level out and have that carrying capacity. And then here you can see under these low food conditions, they still grow rapidly. So there is some exponential growth, but then they reach that plateau when they hit the carrying capacity. All right, and so this brings up another term, which is called biotic potential. So biotic potential is the maximum potential growth rate of a population if there were no, and it's important, if there were no limiting resources. So if we just had an infinite supply of resources, what's the potential reproductive growth rate of this population? And so biotic potential actually is shown using this J curve. It's shaped like a letter J, and that represents exponential growth. And then when we do have this environmental resistance or limiting factors, that's where we get the carrying capacity, which comes into play here. And so we'll initially have exponential growth. This is what it would be without resources. It's showing you the blue dotted line here. But this is when we have competition for resources, and that growth is going to be limited, and we end up with a J curve or an S curve shaped like the letter S. So J, exponential growth, S, logistic growth. So it's rapid growth, competition kind of limits it, it reaches its carrying capacity. Again, we know realistically there's some overshoot and some die off, but on average, we end up kind of flattening out here around the carrying capacity. Okay, so that is biotic potential. All right, how do we calculate the population change? We're going to be doing this a lot in the next kind of sets of notes here, but you need to know that inputs increase the population. So the different inputs involved in population change are birth rate, or the number of births, and the number of individuals that immigrate into an area. Okay, outputs are going to decrease the population size, so that would include things like deaths, number of deaths, and emigration, or that's when organisms leave an area. So population size, to write an equation for this, is equal to the immigrations plus the births minus, and this is a typo, I just found this should say emigrations plus deaths. So it's these things added together minus these things added together. So an elk population of 52 elk has 19 births and 6 deaths in a season. They also have 5 new elk immigrate to the herd and 0 elk emigrate from the herd. That's another typo. Lots of typos today. So 19 plus 5 is going to be 24. 24 minus 6 is going to equal 18 elk. So if the original population had 52 plus 18, we're going to end up with 70 elk. Okay, so that's that. And that's how you would calculate this. Kind of simple. You just have to think about what you're doing. So, all right, practice FRQ. Calculate, this is a percent change equation, and we should all know how to do that. But calculate the percent change in the population size of a 14 individual wolf pack that experiences 5 deaths, 3 births, and 4 new wolves released into the pack from a nearby wildlife sanctuary. Don't forget, you're calculating percent change, so you're going to have to do 2 equations. You'll do the equation I showed you on the previous page, and then you're going to run that through the percent change equation. So make sure you realize that you've got 2 sets of equations that you're going to do there. All right, next time we're going to be talking about age structure diagrams. They're pretty straightforward, so I don't think we'll have any issues with that. But if you had any questions about anything that we talked about today, make sure that you ask me in class, and I'll see you all next time. Have a good one.